The next topic that we're going to be covering is a topic called half-angle identities. We've already discussed the double angle identities in the last section, and now we're going to be using those identities to derive a new set of identities called the half-angle identities. The relationship between these, obviously, if you have a double angle identity, you have an angle x, for instance, and then you have another angle 2x, which is double the original angle. Well, with the half-angle identities, it reverses that. So you would start with the larger angle and cut it in half, find the other angles, right? And so what we're going to actually do is we're going to take a couple of these formulas and we're going to solve for the trig function with the smaller angle, okay? And then we'll be able to come up with formulas for the smaller angle rather than for the bigger angle. All right. So we're going to take the second formula down here, second identity that has the cosine 2x and the sine squared of x in it, and we're going to solve for the sine of x. Okay. So I'm going to start with that identity. We have the cosine of 2x equals 1 minus 2 sine squared of x. And what I want to do is get the sine of x by itself, right? So we're going to solve for sine x. I got to get that by itself. So to do that, we've got to work on everything around the sine, right? We're going to start with the 1. We've got to get rid of the 1. Subtract that from both sides. So we get the cosine of 2x minus 1 is equal to negative 2 times the sine squared of x. Okay. Now I'm going to get rid of the negative on the sine squared. So I'm going to divide both sides by negative 1. Actually, we might as well divide both sides by negative 2, right? Got to get rid of the 2 anyway. So let's do that. I'm going to divide that to both terms. Distributes to every term. The negative attaches to this term. We get negative the cosine of 2x over 2. And here the double negative makes a plus. So it's plus 1/2. Of course, we could reorder these so that the minus is in the middle. It'd be 1/2. Can't write my ones here. 1/2 minus the cosine of 2x all over 2. And of course, on the other side, we just have the sine squared of x. And finally, because these have a common denominator, we could add them together and call this 1 minus the cosine of 2x all over 2 equals the sine squared of x. Now we're not quite done. I've solved for the sine squared. I have not yet solved for the sine. So we use the square root property to get rid of the square. So I'm going to, the square root property basically says that if a variable squared equals a constant, then that variable must be the positive or negative square root of that constant. Okay, so you get both the positive and the negative option. Think about if you had x squared equals 9, then that means x would have to be plus or minus 3. Take the square root of the 9, you could have the positive or negative version. So here, again, with a solving for something being squared, you would take the square root property and apply it. You get plus or minus the square root of 1 minus the cosine of 2x all over 2 equal to the sine. Okay. Now, a couple of weird things about this formula. First of all, you have a plus or minus option that really gives you two possible outputs or two possible values. And that's kind of weird. But remember the sign of a trig function, whether it's positive or negative, is always determined by the angle, or I'm sorry, by the quadrant in which the angle terminates. And so I'll discuss that a little bit more once I tinker with these angles a little bit more. And then I'll describe the quadrant thing. So here, notice that we have 2x under the root, and I have x that I solve for, right, the sine of x. Well, let's say I wanted to have, I want to write it in terms of this 2x angle. I just want that to be my variable. So I'm going to change out my variable here for just a moment. I'm going to let a equal that 2x angle, okay? So this would be cosine of a. Then, if I solve for x here, if I divide out the 2, x would be a over 2, or half of a, right? So, which makes sense. If this angle is double x, then x is half of this angle, right? So this angle a is a, then this is a over 2. All right, so what we're going to do is we're going to make those two substitutions. We're going to replace the 2x with a, and we're going to replace the x with a over 2 in this formula. So we're going to have a new formula that says the sine of x, I'm sorry, not the sine of x. I just said I was going to replace that. Instead of x, we're going to use a over 2. So the sine of a over 2 is equal to plus or minus the square root of 1 minus the cosine of a all over 2, right? Now again, I said I would mention the quadrant idea. So the angle a over 2, this angle here is going to terminate in one of the 4 quadrants. That quadrant is going to determine the sine of the sine, okay? The SIGN of the SIN. And so we know that we have our ASTC diagram. And so if a over 2 terminates in the first or second quadrant, we choose the plus. If the a over 2 terminates in the third or fourth quadrants, we would choose the minus. Okay? So you choose the sign of the sine based upon where a over 2 terminates. So let me summarize that for just a moment. If a over 2, that's an angle, right? It's half of the angle that's inside the root. If a over 2 is in quadrant 1 or 2, then choose positive. Choose the plus. Okay? And I could write another sentence for the minus, but I'm running out of room and I can speak it out just as well. If a over 2 is in quadrants 3 or 4, choose the minus. Okay? Okay, so that gives us a formula. This is called a half-angle identity. There are several half-angle identities. They can be derived in similar ways. So I'm going to summarize those for you here. Rather than going through and deriving all of the details, we'll just derive a couple. And I'll make some notes of the rest. So, oops. I don't want to do this. Let's structure it this way. Let's put it over on the side here. So we have this one now. The sine of a over 2 is plus or minus the square root of 1 minus cosine of a all over 2. And then again, we know now how to choose the sign of the sine. Well, if I were to do a very similar process with a different formula, so if I were to take this third formula with the cosine squared and solve for the cosine, I would get a very similar process, right? You're going to add the you're going to add the 1, you're going to divide by 2, you're going to take the square root property, and so forth. And the formula you're going to get is the cosine of a over 2 equals plus or minus the square root of 1 plus the cosine of a all over 2. All right? Which kind of makes sense because in this formula, what's different from the first formula? Well, the sine versus the cosine, right? So you get cosine, the sine, cosine, whatever. Here the signs are different, right? Here we have a 1 that's positive and a 2 that's negative. Or I'm sorry, the 1 is positive and the sine is negative. Here the 1 is negative and the cosine is positive. And so you have the change in the sign there on the cosine. Yeah, okay, so when you solve for the, right. I said something wrong there. When you solve for this sine, it makes this cosine change sign. Here, it doesn't because it's positive to begin with. That's the thing. So here the cosine is negative, here the cosine would be positive. And then you divide them both by 2, right? So they're both divided by 2. They both have the 1 on the other side. So they both have the 1 in there. That looks weird. And then they both have to take the square root. Okay, so when you solve those, that works out pretty nicely. Now, there is a formula for the tangent. I'm not going to go through and utilize this double angle identity because we have 2 terms with tangent in it, and it gets to be pretty lengthy. There's a quicker way to derive the formula than that, and it is to utilize the quotient identity. We know that the tangent of any angle, is equal to the sine over the cosine of that same angle. So if I wanted the tangent of a over 2, that's equal to the sine of a over 2 divided by the cosine of a over 2. Okay? So I'm going to take these 2 formulas and divide them. Now what do I do with the plus minuses? Well, because the pluses and minuses could vary based upon the quadrant, the sign of the tangent could also vary based upon the quadrant. And so we're going to include both the plus and the minus because the tangent can be positive in the first and third quadrants and negative in the second and fourth quadrants. Okay, so we're going to include the plus minus. When you divide 2 roots, right, a root divided by a root, you can combine them as one fraction. So this could be the square root of the top, 1 minus the cosine A over 2, all over 1 plus the cosine of A all over 2, right? So I can put them both under the same root. And then, if you multiply by the reciprocal of the denominator, so copy dot flip, you'll end up with 1 long root, 1 minus the cosine of A over 2 times 2 over 1 plus the cosine of A. And of course the 2's will cancel, and you end up with plus or minus the square root of 1 minus the cosine of A over 1 plus the cosine of A, right? This is a nice simple formula. It only involves the cosine, which is even nicer. We don't need both the sine and the cosine for this. And that's going to be one of our formulas for the tangent. All right, so I'm going to erase the derivation here. And just put that formula on the board. All right, so there's another formula. Now there are some other formulas, half-angle formulas. The first one, again, there are other formulas for the tangent. So the sine and the cosine ones are kind of set. And one thing I want to mention is I chose the 2 formulas here with the sine and the cosine because they only had one of the 2 functions, either sine or cosine. I didn't choose the top one because it involved both the sine and the cosine. That's harder to solve for. So did this formula for the sine, right? It involves both the sine and the cosine, so you can't really isolate one of them over the other. Now there are other ways, other formulas for the tangent. So let's take a look at those. The first one is again to start out with the tangent of a over 2 being equal to the sine of a over 2 over the cosine of a over 2. All right. Now, if I were, if I were to make kind of a strange, clever algebra trick here, I'm going to multiply this fraction by 1. If I multiply by 1, it doesn't change things, right? The form that 1 is going to take is going to be 2 times the cosine of a over 2. As long as I do that to the top and the bottom of the fraction, it doesn't change the value of the fraction, right? I'm just multiplying by 1 essentially. So, when I do that multiplication, and again, this is just a kind of a clever mathematical trick. We're just utilizing this particular expression of 2 cos alpha, or a over 2, because it's going to work well for us as we go. What we're going to end up with is 2 times the sine times the cosine. So 2 sine a over 2 cosine a over 2 all over 2 times the cosine squared a over 2. Okay? Now, at this point, I don't want to simplify. My temptation is to cancel the 2's here. It actually went through my head, but I put those 2's in for a reason, so I don't want to cancel them out. Instead, I'm going to use the top of this formula. 2 sine a over 2 cos a over 2 looks a lot like the right side of our double angle identity. In fact, it is the right side. And so, but notice, here we have x's, here we have a over 2's. But remember, x and a over 2 were the same a couple formulas ago, which meant that 2x was a, remember? That's where we got that relationship from. If x is half of 2x, then a going in here would be half, or would be twice the a over 2. So what we're going to do is we're going to replace that top expression with the sine of a. Right? Because the sine of a, remember, this was the a, and this was a over 2, and this was a over 2. Right? So that relationship holds. On the bottom, 2 cosine squared of an angle is this expression right here. And so if I were to add the 1 to both sides, replace the 2x back with the a again, I would have 1 plus the cosine of a. All right, so I get sine a over 1 plus the cosine of a, and that's using 2 of our double angle identities. Okay. This is a new expression then for the tangent of a over 2. So we have tangent a over 2 equals the sine of a over 1 plus the cosine of a. All right. Notice with this formula, I don't have the plus or minus anymore. And that's because the plus or minus will be determined based upon the signs of the sine and cosine. Okay, so when you start plugging stuff in here, you'll get the tangent to work out properly. The other thing, the other formula comes from a little trick that we can do with this formula. We can multiply the top and bottom by the conjugate of the denominator. Okay, the conjugate. Now, we've done this before, but in different contexts. If we multiply, again, this is another little trick like we did up here. If I take this and multiply by 1 minus the cosine of a, and do the same thing to the top. Again, I'm just multiplying by 1, right? It's the same thing over itself. So it's not going to change the value of this fraction, just what it looks like. Then I'm going to leave the top in factored form. That's strategic. There's a reason I'm going to do that. In a moment, we're going to be able to cancel some stuff. And on the bottom, I'm going to actually distribute this. Now, when you multiply two conjugates together, you get the difference of squares. You get the difference of the first term squared and the second term squared. And if you wanted to use the FOIL method or distribute here, 1 times 1, 1 times negative cosine, and so forth, you would get the same thing, okay? And so here, 1 minus the cosine squared is one of our other identities, a Pythagorean identity. Remember that the sine squared of an angle plus the cosine squared is equal to 1. So if you subtract the cosine squared off from both sides, you really get the sine squared. So this thing down here, based upon a Pythagorean identity, is the sine squared. And so we end up with the sine of A times 1 minus the cosine of A all over the sine squared of A, right? That's a Pythagorean identity. And then I can cancel. I've got sine over sine squared. Oh, I put an x. I want that to be an A. There we go. Sine over sine squared reduces, right? You can take one of those powers off. And what we'll end up with is 1 minus cos A all over the sine of A, right? So I'm going to use that as my next formula. The tangent of A over 2 is equal to 1 minus the cosine of A all over the sine of A. And so now we have these 5 formulas that help us to find trig values for half of an angle if we know the larger angle. This could help us to find, say, something like the tangent of 7.5 degrees if we knew the cosine and the sine of 15 degrees. If we know one angle, 15, you can then find trig values for half that angle, which allows us now to find a whole slew of other angles that we haven't been able to identify exact values for yet. Okay, so we've seen the sine of 15 degrees, the tangent of 15 degrees when we did our sum and difference formulas, but now we're going to be able to find even more angles. Chop that in half, and you'll be able to find more expressions for those angles based upon these formulas. Very useful formula. You could find, the cosine of 22.5 degrees if you know the cosine of 45, which we know the cosine of 45. So now we can plug those things in, which we'll be doing in the next couple videos when we go through some examples.